Okay, so thank you very much, everyone. Apologies for the technical glitches there. Um, so it's a pleasure to be with you this afternoon. My name is Phil Legg. I'm Professor of Cybersecurity at University West of England. I'm going to be talking today about artificial intelligence, agents, and what does it mean for cybersecurity. Okay, so just a little bit of background of myself. So, as I mentioned, Professor of Cybersecurity. I've been at UWE for about 10 years now. I'm the co-director of UE Cyber, which is our NCSC Academic Centre of Excellence in Cybersecurity Education. And I'm also the cybersecurity research lead for our Computer Science Research Centre. In terms of my research interests, obviously cybersecurity is very much in there, and I'm interested in how we use machine learning and data visualization to better understand cybersecurity challenges. So previously, before I joined UE, I was working with the Centre for Protection of National Infrastructure, looking at insider threat detection systems and building machine learning models and visualization platforms for being able to recognize essentially malicious behaviors in corporate organizations. Also interested in how we better understand cybersecurity in terms of situational awareness, how adversarial AI can play into this to be able to circumvent systems which are designed to recognize malicious behaviors. Also, more recently, interested in privacy preserving methods of AI. So, how can we, actually look after the data of individuals whilst being able to develop systems that learn characteristics about that? And also thinking about things like explainable AI. So, again, it ties into how do we make better informed decisions when we're talking about cybersecurity and when we're talking about how AI plays into cybersecurity. Couple of projects that I've been involved in. So I've done things on connected autonomous vehicles, looking at security properties of an autonomous bus, which was part of the CAV4 project. I've looked at IoT devices across cityscapes. So as part of the Umbrella project, we're looking at how we collect telemetry across a cityscape and how we recognize anomalies in that environment. I've done work with Avon and Somerset Police and an organization called Synologic around uh, how we better triage crime reports. So, if we've got online fraud activity, for instance, can we use things like AI techniques to actually classify and triage reports quicker and more effectively than traditional methods? And as well as that, again, as I mentioned already, looking at things like AI security with various SMEs in the region. As I've mentioned, a big part of my work is around this idea of effective real-time decision making to help address cybersecurity issues, informing both human and machine operators. So we often talk about things like human machine teaming, for instance, and this is very much how machine learning processes can complement what we as humans can bring to the table. And I think, certainly in the last couple of years, what with developments around large language models and the like, that we'll be talking about later on today, you know, there has never been a more important time to think about how humans and machines collaborate effectively to be able to achieve these kind of end results. Finally, just as a bit of a recap on UE Cyber and the kind of research that we look at as a team, there are typically three strands to our work underpinned by pedagogy. So we look at things like software and cloud and infrastructure security. This is everything from container-based security, software security, IoT, and CAV. We've got cybersecurity data analytics as a key part of our work. A lot of people look at cybersecurity and AI and how you can kind of use that to better understand data. Data is fundamental when we're talking about security. So this is where we think about machine learning for the purposes of security, but also the security of ML and AI processes, as well as the privacy, transparency, and trust in these processes as well. And then there's this kind of cybercrime and domestic cybersecurity strand, which is more about how how all of this helps the general audience, the wider public. So this might be things like online harms, forensic analysis, dark web investigations, all the way through to financial crime and geopolitics. And as I mentioned as well, we're very interested in pedagogic research around cybersecurity. So, as educators as well as researchers, what does make for effective interactive teaching of cybersecurity? Um, this is a bit of an open challenge in many ways. As practitioners and educators, we try lots of things, but it's very much, we're interested in exploring what's effective for different types of learners. Okay. So I'll bring us on to today's talk. And as I say, I want to look at artificial intelligence, a term which we're hearing a lot about in the media and general society outside of just the scope of computer science domains that we're based within. We're going to look at agents and we're going to think about, well, what does it mean for cybersecurity? And so this touches on that idea of how we use AI for cybersecurity, but also how we think about the security of AI systems as well. So you probably don't need me to introduce the term GPT. We hear the term GPT quite a lot nowadays, especially when people talk about Chat GPT. It has become synonymous with AI as far as the wider society and public are concerned. But I think it's really useful to just think about what we're talking about. So this is generative pre-trained transformers. And actually, we've been talking about GPT models since 2018. Um, so GPT-1 was released in June 2018, trained on 117 million parameters. November 2019, we had GPT-2, trained on 1.5 billion parameters. Okay, so a significant jump already. June 2020, we see GPT-3 trained on 175 million parameters. And this is then getting into the stage where this starts creeping into our everyday lives. ChatGPT was publicly released in November 22. And since then, there's been a whole bunch of these GPT models. Okay. And we now typically think of this as large language models. But essentially, what we're talking about is a machine learning model that is able to generate language, so generate the next word or character or more likely token within a string of tokens. And we're able to do this using a method called transformers. Okay, we'll touch a little bit more on the term transformer shortly. We've also got this idea of online and offline models. So online models, the things you'll be familiar with, OpenAI, Microsoft, Google Gemini, a bunch of other ones out there. But these are third-party services being hosted online. Anyone can log in, ask it a question, it'll give you a response. We've also got offline models becoming more and more popular. These run locally, so it's a trained model. We might have something like a GGUF format, GGUFF format even. But we can actually download the model weights locally. We can run that model locally. And the benefit of this is that although it might not necessarily perform as quick as using a cloud service, for instance, we can at least keep our queries private, keep our data private. And so, this is gaining a lot of popularity in terms of how we as practitioners can start to use some of these systems. So again, ChatGPT, I suspect everyone on the call is fairly familiar with this. For those who aren't, essentially we've got a conversational chatbot. So I'm able to ask it a question or ask it a request of this system, and it's able to produce some sort of response. So here, for the purpose of the imagery, write me a poem about cybersecurity, and I get this lovely poem back, The Guardians of the Digital Gate. Okay, so it's there. You can take a look through this, but it's pretty impressive what it's able to generate in a relatively quick period of time. Um, it rhymes, it acts as a poem, it seems perfectly reasonable, it's on topic. So actually, it's a pretty impressive response that is returned by this chatbot. But essentially, what's happening under the hood is a prompt is given by the system saying, write me a poem about cybersecurity. And then it's asking the system to think, right, what would the next suitable word be in this sequence of words? Okay. We can think of this as tokens. So traditionally, we would have used words and we might have said, given the words, the cat sat on the, what would be the next word here? We might say Matt, a popular phrase that has been recorded in many, many places. So statistically speaking, if I had the cat sat on the as my words, as my input, Matt could be a sensible output based on the statistics of that being a common phrase that has occurred previously. So this is essentially how these models are working in the sense that if you've then scaled your data collection to be the entirety of the public internet, so that you've got patterns of co-occurring words, then if I could, for any given input, what is a sensible output? It's able to statistically reason to say this is the next word that should come in that sentence. So it's trying to predict that next token. And the reason why I'm using this term token, for those who may not be familiar with it, is that words are okay, predicting the next word is okay, predicting the next character is okay, but not necessarily perfect in either scenario. If you predict the next character, you might get caught up in a system where it's then producing gobbledygook and not actually constructing real words. And if you ask it to produce complete words, then you might get trapped in a system where it's not necessarily bringing in creativity and nuances that you might want in your text. So the idea of a token is something that's possibly longer than a character, but not necessarily as long as a word. So some words you might break down into multiple tokens to be able to bring in just a bit more variation of how the words are constructed. And the context is maintained by this idea of a transformer model. And the transformer model came about in about 2018, I believe it was. And this is key for maintaining context. As I say, you can have this system where given an input, we predict the next word, and we can keep on doing that and keep on doing that. But how do we ensure that, if the system has essentially produced a sentence, how do we ensure that the next sentence follows on and makes sense? It carries on the same kind of topic and flow. And this all comes down to a model called transformers, where it's essentially able to better maintain that context of what was being discussed previously. Therefore, what should we be discussing going forward? The classic example is if you're talking about withdrawing money from the bank versus sitting on the bank of a river, how do the words around that word bank help you infer what the meaning of that word is? So this is a model known as transformers. Before that, we might have used things like LSTM models, so long short-term memory models or recurrent neural networks. But it's the transformer model that really brought in the ability to understand context over an extended period of time, or in this case, an extended sequence of words, such that context can be maintained and therefore, where the sentence started and where the sentence ends or the paragraph ends still remains relevant to what was being asked. Okay, so that gives you a simple example of being able to um, generate a response. So having a conversation and being able to say, write me a poem. Okay, here's a poem. And the neat thing that we see with things like ChatGPT and other models is the ability to do this for code. If we can do this for the English language, we can do this for other languages effectively that have been incorporated in the model. All of these models are essentially trained on mass corpuses of text that are scraped from the internet. So, by its very nature, then, if you imagine scraping the entirety of GitHub, you'd get a lot of software source code and obviously, other source code available on other websites. So these models have become extremely powerful for being able to generate code. And again, this is an example which some of you may well have tried playing around with. But here I can say, write me a Python script to play Pong, and immediately I get a nice description included with code, um, where I can then run that as a Python script and actually deploy a game of Pong, in seconds, essentially. I can also then use this to refine and tweak my code. So, if I say, oh, well, I didn't want a black and white environment, I want to make the paddles red and blue, I want to make the ball green, I can talk to it quite freely to be able to have the system understand what I'm requesting and make the changes in code. So, again, we're still talking about having a conversation at this point, but I can have a conversation about, can you generate some Python code in this example that allows me to achieve the task I'm interested in. So we were talking about tokens, and essentially all of this comes down to token prediction. And there's a nice tool on the OpenAI website where you can actually give it a body of text and see how different models such as GPT-4, GPT-4o would actually tokenize that text. Okay. So essentially what all it's trying to do is recognize, given a set of tokens, what would the next token be? And it's trying to do this over and over and over again. It's important to recognize essentially each of these tokens maps to a numerical value. So in this example, I've just taken the first three parts of the poem it generated earlier, and I can see actually, the array representation of what that poem looks like. So the numerical values are giving me references to what the text tokens are. And so it can work out, oh, well, if I've seen 637 followed by 142, 945, then the next one must be 120,452. Essentially, it's working out which of the tokens should follow next based on what it's been given to start with. And it's important to recognize that the numerical underpinnings of this, I mean, as end users, we interact with these systems via text, the natural language that is so common to us. But underpinning that, the system essentially is creating a series of numerical reference points that represent that text, and then saying, given this string of numbers, which number or which reference should follow next. So then just on wrapping up the point about LLMs, there's some very interesting research papers that have been coming out. So just to flag up this one, when LLMs meet cybersecurity, a systematic literature review, they're covering 300 papers since 2023. So it really is interesting just to see the sheer scale that is being published in this space in terms of how LLMs are being used in cybersecurity. And we're seeing things from vulnerability detection, secure or insecure secure code generation, program repair, binary analysis, IT operations, threat intelligence, anomaly detection, um, LLM assisted attacks. There's a whole bunch of things, but it's a very active area at the moment. Very challenging to keep up in this area, in all honesty. But nevertheless, this was a very good literature review, systematic literature review that covers some of the interesting areas where LLMs are being applied to. And I wanted to just introduce these two papers as well. So we've got cybermetric, which is essentially a data set of 10,000 cybersecurity questions, fundamentally, the kind of thing you might find on things like a Security Plus or a Pen Test Plus exam by CompTIA, and essentially seeing how well can LLMs answer these questions. The answer is they can do a very, very, very good job on them. Um, so as a knowledge bank, LLMs are really powerful in terms of cybersecurity. If I've got a piece of code and I want to say, can you identify the bugs in this code, or you know, can you identify what kind of vulnerabilities might be present here? LLMs are proving to be able to do a very, very handy job of this. Another one that's interesting to flag is harm bench. So here now we're talking about a data set of malicious queries. Now, there's a whole gamut of topics covered by harm bench, um, from things like how do I curate a bomb, or how do I do things that I shouldn't be doing, all the way through to how do I how do I generate malware, how do I DDoS an organization, whatever it might be. All the kind of things that we wouldn't really want an LLM to be answering. Okay, we don't really want anyone to be answering. They're essentially harmful behaviors. But the purpose of the data set is really to be able to assess, are appropriate guardrails being put on to stop the generation of responses to these kind of questions. Because then it's interesting to be able to see, even if they have put guardrails up, are there ways of subverting the model to be able to get the answers out again? And even with guardrails up, what this paper and the associated data sets allow us to see is actually a lot of the guardrails can be circumvented. Um, it's going to become an increasingly challenging area to really prevent LLMs from generating responses to malicious queries. But again, a really interesting area of research for people that might be wanting to explore that. Okay, let's talk about agents. So, what is an agent? Well, an agent performs actions to learn about their environment. So, the term agent has been used a lot with, multi-agent systems have been a thing in artificial intelligence for many years. Reinforcement learning is essentially about agents and how they act in an environment. So we have these things called agents, okay? And an agent is able to perform this action, and this has some impact in the environment, and it then changes some state about that environment, okay? Based on that action, there may or may not be a reward earned by the agent, the user. I mentioned game-based reinforcement learning here because it's an easy to understand example, but it's also an area where reinforcement learning has been used massively in the past. So a prime example is you give it a game of Super Mario and you say your actions are constrained to what's on your control pad. You're allowed to go, left, right, up, down, jump, and see how far the agent, Mario in this case, can progress right. Essentially, you have to run right as far as you can and get to the flagpole. So if you set your reward function to be, well, what distance did that character travel when they perform this set of actions? Um, that becomes your reward function. Now, when this thing starts off, it doesn't know what going left or right is going to achieve. Okay. It has no idea. All it knows is that reward function as a value. It doesn't even know what helps it increase that reward value. It just knows that these are the actions I can perform, and something will happen that allows me to increase that reward value. So, using trial and error, so being able to reset this environment, start from scratch, play it out again, it can start to learn, oh, if I go right, that helps to increase the reward function. If I continue to go right, that helps to increase it further. I get hit by a Goomba or whatever it might be, and that ends the game. So then over time, it learns to be able to jump over the Goomba to be able to keep on increasing that score. So, again, it's learning about its environment. And this has been used in GPT for being able to do reinforcement learning with human feedback. Okay, so this is essentially the models will generate some responses. Humans will respond to say whether or not these are appropriate for the question that was being asked. And over many, many iterations, they're able to refine and improve their responses. But reinforcement learning, if you're interested, there's a couple of links. It's a fascinating area to look into. So then, what does this mean for large language model agents? So we're hearing a lot at the moment around this idea of LLM agents. So we've already been talking about this idea of an agent being able to learn about its environment, being able to take actions, and being able to get a reward for that. And we've seen before that, this idea of being able to ask questions of an LLM and being able to get a response. So we kind of take those two ideas and we blend them together a bit. So given a task or a question and given a set of tools, that's like the actions that we were talking about with reinforcement learning, and an environment, can the LLM provide a suitable answer? So if we see on our diagram here, then we've got our task, our question, we're posing that to our LLM, and then it's got to decide, well, can I answer this question? Or, in fact, do I have access to some action or some tool that allows me to do an even better job of answering the question? So there's a concept called tool cooling. Tool cooling. Yeah, it's a bit of a mouthful, but tool cooling. It allows you, the LLM, to determine, does it know about a suitable tool? And does it know the schema or the API usage for being able to access that tool, gain a response, and then conduct further processing? So this ties into a framework known as React. So this is about reasoning and acting. So the LLM is able to reason to be able to come up with a series of steps that it might follow to be able to conduct, well, to be able to provide an answer. And then if it's able to reason about what are the suitable steps to take, it then tries to act by saying, do I have a tool available to me that it enables me to complete that step in my reasoning process? Okay. So as it says over here, language models themselves can't take actions, they just output text. But things like a LangChain, okay, so LangChain is a library that allows you to develop LLM agents. They bring in this reasoning ability to be able to say, I've determined that I can use a tool, and that allows me to make some requests to some other service that can allow me to accomplish that task. Okay. So again, if we see on this figure, we've got this LLM performing this reasoning. It looks to the tools that are available. And then based on the tools that are available, it may take an action in the environment. And that will obviously then give some result back. It can continue to do this if it feels like further steps are required, or if it's satisfied that it's got a result, it can return that back to the LLM. That can then essentially conduct the reasoning to say, have we got a suitable answer to that question? And then feed that back to the user. So if we think about something like this, where we've got a user, they pose a query to the model is going to decide whether or not to call a tool. If so, it will initiate some API request to that tool. That tool will then, well, that API will then give a response back to the model, and the model will construct a final answer to return to the user. So, as a simple idea, what is the weather like today in Hawaii? Now, again, recognizing how an LLM works, LLMs essentially started out by scraping all of the publicly available data from the internet, and then being able to say, right, I've trained a model as of whatever date they claim. and it can tell you information about all things up to that date. But what it can't necessarily do is tell you about something that's happened after that date. So asking it a question, what's the weather like today in Hawaii, might seem like a really simple question. But fundamentally, if it's not in the the training data, you know, it might be able to tell us something like typically Hawaii is quite hot this time of year or something to that effect. But it wouldn't actually be able to tell us by itself with certainty what the temperature is today because it doesn't know. It doesn't, that information is not available to it. So this is where it says, well, okay, if I don't know that information, do I have a tool that allows me to gather that information? So here we might have some query that says, right, let's get weather. The location is Hawaii. We're going to use a search tool. So that could be, sending an API request to weather.com or whatever it might be. And that tool is able to return a message such as 85 degrees Fahrenheit and sunny. Okay. So that content gets passed back to the LLM, back to the model, and then it's able to construct a final message back to that user. Hawaii is 85 degrees Fahrenheit and sunny. Okay, relatively straightforward example, but it demonstrates this idea that if the LLM itself thinks, actually, I don't know the answer to this, or at least I've got a suite of tools available to me and I could use a tool here. This is a simple example of being able to make a request to some external tool, get a response back, and then use that response as part of the answer that is returned to the user. So then that's if I've got a lookup service like weather.com or something like that. Now let's think about code execution. So what if our tool was essentially a Python code interpreter? So rather than just looking up to, weather forecast API, if I've got a Python interpreter, then my LLM, we've already seen earlier, it can generate Python code quite easily. Can it then execute that Python code and get a response and then return that response as well? So this is where LLM agents become very, very sophisticated at this point. So rather than having an LLM generate the answer directly, it can be better to have the LLM generate the code to calculate the answer, then run that code to get the answer. So LangChain, I've mentioned already, is a popular library for being able to generate these LLM agents. There are other tools available. AutoGen is one put out by Microsoft, a bunch of others, no doubt, creeping onto the scene as well. But if I just look at LangChain as the example here, it actually had a tool built in called Python AST REPL tool. So this effectively gives you a REPL environment where you can give it a Python command, it will execute that command, and it will print out the output. Another one which builds on top of this is create pandas data frame agent. Now, for those who may not be aware, pandas data frame, that essentially is a way of storing CSV data or just tabular data, popular in the data science community that use Python. So now this gives me an agent that is able to interact with pandas data frames. And if I've got a data frame, I can do all sorts of calculations and analysis on that data using an LLM. It is worth saying, use with care. So what is happening here is, previously we've put a request in, for instance, on the OpenAI example, we put a request in, that request gets sent to their server. They then run that through the model and return an output. What's happening here is ever so slightly different in the sense that I'm putting forward a task or a question. The LLM is using a tool to come up with what an appropriate response would be. But what it's going to do in this example is generate the code that should be used, and then it's going to run that code on my local system. Okay, so on my data frame, for instance, but it's going to actually execute the code that has been generated by the LLM on my system to then see the output of that code and then perform further reasoning as and needed. So there is this parameter that is used within LangChain. Allow dangerous code must be set to true. Okay, so it is false by default. It must be set to true. So, straight away, you're kind of thinking to yourself, this is some interesting territory because we're now giving the LLM free rein to execute any Python code it can generate on my machine. Okay, so that leads us nicely on. What does this mean for cybersecurity? So cybersecurity data analytics, as I mentioned at the outset, there is a lot of people interested in cybersecurity data analytics. There's a lot of data involved in cybersecurity, whether we're talking about network traffic analysis, malware analysis, user behavioral analysis, all these kind of things. We're dealing with a lot of activity data. How can we better understand that data, better filter it to be able to identify the things that really matter to us as analysts? So, can an analyst identify suspicious user behavior? So, the question then becomes, well, can an analyst use an LLM agent to help support the task of human machine teaming, human machine collaboration to better analyze their data in a rapid way? So, we've done some work on this and found some really, really quite interesting results as part of the preliminary studies. We've been using Jupyter Notebook environments. So Jupyter Notebooks are very powerful concept um, within Python and other languages, I guess. Essentially, it gives you a way of writing code, but in a cell-like structure. So you haven't got to write the entire Py file and execute everything all at once. You can actually execute code segments incrementally. That's really useful when you're trying to analyze and observe what's happening within a workflow. But it also actually ties in really nicely here because it's like having a conversation with the code. So again, thinking about the ChatGPT interface where it's question, answer, response. Here I can give the system some code in a cell. I get a response. I can then think, right, what do I do next? What do I want to follow up with? We've been looking at CSV data sets, in particular around insider threat data and web server logs. So there's two tools in particular. Carnegie Mellon University have an insider threat data set that they make, well, lots of different insider threat data sets that they make available. And there's also a tool by Punk Security called Pwn Spoof, which allows you to generate interesting CTF style challenges around web server logs. And so what we've been playing around with is essentially how well could LLM agents actually solve these challenges? So being able to recognize insider threats, being able to recognize security issues within a web server log. So you get this kind of thing. So here's just a brief example of a code cell. So here I've got some text that I'm giving to my LLM agent. I'm telling it about the data that I'm using, and I'm asking it, well, what websites do directors typically visit? And what it's able to do is access the data frames on my local system, run the Python commands effectively for being able to do value counts and things like that on my data set. It's able to then identify what the outcome was, what the output of running those commands was, and then it gives me the kind of prose response of what it's found. So in this particular example, it's interesting to see that of all of the directors in this data set, legaleagle.com and LinkedIn were both accessed 5 times each by this particular user. All these other websites were accessed many more times. So This tells me something about how infrequently these websites were accessed, and does that raise suspicion that they might not normally access these websites and now they've suddenly accessed them. Other things like this, I'm able to see how many times does a director insert a USB device. So here it's telling me about this particular user that's accessed the USB device 4 times. And it's not told me about any other directors because none of the other directors actually did it. So again, it's starting to show to me what are the behaviors that one individual did that other individuals didn't do. Okay, just mindful of time, so I'll move on a bit faster. Um, Again, just looking at some of the outputs, it's worth me saying there is a GitHub repository for this. It is private at the moment, but if people are interested in this, please email me afterwards. I'm happy to share access, and it will become publicly available when the papers are published on this work. But here then is an example of being able to look at the web server logs and recognize what the suspicious activity was. So here are four different users who were observed to actually flag up 401 status errors. So recognizing that there had been incorrect password attempts made by those IP addresses on this particular web server. So it's indicative of a brute force password attempt. Here we had different websites being accessed, then actually there was a command injection attack taking place. So within this particular column, so the query being given to the URI, the LLM was able to identify some suspicious activity where the percentage character was present, and it's able to then explain what's actually happening stage by stage. Now, again, I mean, whilst you could say, oh, well, yes, you could filter that and identify that, the powerful thing here is that we've just said to this, here's a data set. Is there anything suspicious in here? And it's able to identify this based on looking at all of the columns and working out, well, what looks different in comparison to the rest of the data in those columns. In this example, this is the insider threat data set. What's particularly interesting of this one is that this is no longer working with a single CSV file. This is working across 5 different CSV files. So it's able to actually start to correlate and correspond data across the different activity logs that are being recorded for each of the different domains, the login, the email, the web, the USB, and as well as the LDAP records. So the one thing I would say about this is we do have to guide it a little bit in terms of that conversational flow of, oh, well, tell me about this user, tell me about that user. Oh, I found this thing for these directors. This looks interesting. I'll probe further. However, in theory, you could actually have the LLM explore all of those possibilities, and it kind of generate its own hypothesis testing. So what if the agent generated all possible hypotheses automatically? Of course, there is a trade-off here. I skipped it when it was on the slide earlier, but all of this is being done using OpenAI GPT-4. So it is making API requests to retrieve the code samples. So it's using an online model. And so each of those requests comes with a cost. Now, given that you're using it as an agent rather than just give it a question, it gives you a response. And remember that we had that loop. What this means is that actually, if the agent was given a task where it decided it still had further steps to take, it can essentially keep on going and burn through a lot of money very quickly. So I would say if you are looking at developing this kind of stuff, just use that with caution. So this is something we'd love to test in the future in terms of can it generate all possible hypotheses and explore them all? What we don't know at the moment is effectively how much that would cost. But the key thing is, so LLM agents, I mean, there's a lot of buzz, a lot of hype about them at the moment, but they are rapidly being adopted. Okay. We've seen examples here today of being able to do code generation and being able to do code execution using LLM agents. So if I can execute Python code using this, then fundamentally I could actually execute any sort of code using this. Um, we're in discussion at the moment of how can you use this to essentially jailbreak some of these constraints and be able to perform actions on the system. So again, if you think about poisoning an LLM and being able to poison code requests, so it says, oh, instead of giving you back commands about Python or pandas, give them commands which are well, XYZ, which might have some detrimental behavior on your system, then tasking an LLM agent to go off do this coding and then find that it's actually just performed something that you didn't want it to perform on your system could be problematic. Um, so we mentioned that use dangerous code tag earlier. At the moment, it just allows a true or false. We probably need something a bit more granular there to actually say we're allowing these kind of behaviors in code, we're not allowing these kind of behaviors. So just a few kind of key points to finish up on then. How do we validate the actions for more complex code tasks? What if that model is compromised? What if it's, been poisoned in such a way where it's trying to give you malicious code samples embedded within your agent? So all of this ties back to things like software supply chain security. It's a massive risk. It always has been. It's been increasingly so recognized over the last couple of years. And with things like AI, GPT models, and LLM agents, really starting to take off in the public domain now, it's only going to remain an even bigger problem, to be perfectly honest. The offline models, they do help to some extent. They help maintain the privacy, they help maintain a bit of control. There is a trade-off in performance, but we've done work on being able to take some concepts from well-trained models, use that to help improve an offline model. There is probably more work to be done in that space. Offline models, I'm a big fan of. I think if people are going to use this stuff properly, then looking after your own models and knowing what's happening locally is probably the best course of action. We've got this reasoning and acting framework that we mentioned already. Again, it's really interesting to see how the space of reinforcement learning has been growing. Um, we've already mentioned our examples are around Python commands and being able to do pandas, data frames, actions, but that could be any Python command. And if you start then thinking about sub-processes and the like being called from a Python environment, you could actually escape that, get onto the terminal or just the system in general. And what other commands could you be calling? And then you've also got this idea of multiple agents. Okay, so how would this work if you had multiple agents acting together? So it's a rapidly evolving area. We talk, when people say that, it's a little bit like, we've been talking about agents for a long, long time in actual fact, but this gives almost a new lease of life to agents in terms of increasing that action space because now our action space is effectively informed by natural language rather than having a constrained set of actions like the games controller example. But it's a rapidly evolving area. We've got to be thinking about what's the security that we're building in these things, as well as how is AI going to help with security problems. So with that said, thank you ever so much for listening. Please, if you want to get in touch, my email and UE web pages are available there. You can also follow me on LinkedIn and you'll find my personal page at the bottom there as well. So thank you.